Hello, welcome to Linear Algebra, Chapter 1, Section 1, the beginning. I'm Robert Gardner of ETSU, Dr. Bob, if you like, and today we're going to start vectors, matrices, and linear systems. We're going to look at some real introductory concepts concerning vectors. Over the next few months, presumably, we'll see vectors take on lots of different forms. The primary form is that we're about to introduce, is vectors in Euclidean space. The textbook motivates the study of vectors. The properties, the definitions are largely motivated by physical models. You encounter vectors as magnitude and direction, and there's a great deal of legitimacy for that. And there's also some settings where that's an inaccurate concept of vectors. So let's get things rolling with a note or definition. Euclidean one space is simply the line. We're going to denote it with this sort of double blackboard font, R, for the real numbers. So this is just the real number line that you've encountered in high school. Euclidean two space is the collection of all ordered pairs x, y, where we take x and y to be real numbers and denoted commonly with this blackboard font with a superscript of 2. This R2 thing, this is just a Cartesian plane that you encountered also in high school. And in algebra, you spend a bunch of time with it in calculus, because when you graph functions in R2. Most things, when you graph them, functions or not, you graph in R2. Take calculus 3, you'll probably deal with graphs of things in higher dimensions in R3, usually. So you're familiar with R, or R1 and R2. So we just want to take this idea and generalize it to higher dimensional spaces. Sit tight, the term dimension won't be formally defined here for a few sections. So our first definition, our first formal definition, the space Rn, or Euclidean N space, is either one of the following two interpretations. So this is a little bit informal, and it's the second interpretation that for us will be the most useful. So Rn is either the collection of all n tuples of the form, parentheses, x1, x2, up to x sub n, where those x sub i's are all real numbers. In this case, these n tuples, these things here, are called points in Rn. Or an alternative definition of Rn is the collection of all n tuples of the form square bracket, x1, x2, up to x sub n. The x sub i's are real numbers, and in this case, the n tuples are called vectors. So, arguably not a formal definition. We haven't put any structure on it yet. We'll see there's really a lot of conceptual difference between a point and a vector. Maybe you've heard vectors said to have magnitude and direction, but they don't have location. Well, points don't have magnitude, they don't have direction, but they certainly got location. So, to be elaborated on at great length in the future, there's a difference between points and vectors. We haven't stated that difference just yet, beyond the fact that we're using parentheses to indicate points, and we're using these square brackets to indicate vectors, as does Fraley and Beauregard in the textbook that we're using. Not entirely universal. It's not at all uncommon to represent vectors using the parentheses, which is fine unless you're mixing points and vectors in the same setting, and then you don't have a notational way to distinguish between them. But we're set for us, if it's a vector in Rn, then we'll definitely be using the square brackets notation. So R1 is just a collection of real numbers, the real number line. It has an algebraic structure, addition and subtraction, say, multiplication and division, except by 0. So there's algebraic structure to R. It's the idea of addition we want to really draw attention to. as we deal with Euclidean in space beyond just R1. R2 is a collection of all points. If you want to interpret it as a collection of points as opposed to vectors, a collection of all points in the Cartesian plane. So for us, so far, no distinction between points and vectors as yet. Oh, well, we're going to change that here pretty soon. Our only distinction is notational so far. In the book, as is commonly done, this is a common convention, vectors are denoted with boldface letters. So it's common to indicate vectors with boldface letters. What I will do in handwriting things and in typesetting things, and you need to do in handwriting things, is use little arrows over letters to indicate that we've got vectors. And you can't really handwrite a bold-faced font. So we'll indicate vectors by putting these little arrows on them: vector x, vector y, vector v, vector w. And this is how we'll distinguish vectors from other things. The other things we will have will be points. We won't indicate points with little arrows over them because that's what vectors are. We'll have numbers, scalars we'll call them, and we won't have the little vector arrows over the scalars. We might have x the scalar versus x the vector. So there's potential for confusion, so we need from day one to have a good notation that'll allow us to distinguish between the different things we're talking about. Those things will be largely vectors and scalars. We'll want to drag points into the conversation when I want to draw pictures, when I want to see stuff, when I want a geometric interpretation. It'll be convenient to have points. So we'll certainly go running for geometric representations in pictures as often as we can. All right, a little more verbiage. This class is quite heavy on definitions and verbiage. The concepts build up. There's, I want to say, surprisingly few different concepts in here. The stuff we do early on in chapter 1 will come up again and again and again and again in new settings in the following chapters. So the concepts we're about to develop here, they're going to carry us a long way. There'll be lots of other verbiage, but the ideas even later on will largely be based on the stuff we do in chapter 1. You got to get the hang of chapter 1. Definition for x vector in Rn. How you know it's a vector? Because it's got a little arrow over it. For vector x in Rn, say vector x is written as this n tuple, n entries here. The ith component of x is the number x sub I. First component, second component, and so forth up through nth component. So still not a lot of difference between points and vectors, but points don't have components, points have coordinates. So there's more verbal distinction and notational distinction between points and vectors. So vectors have components, whereas points have coordinates. Yet they seem to be otherwise virtually identical. Yes, because we hadn't done anything with the vectors yet. We're going to put an algebraic structure on the vectors because this is linear algebra. And that's where we'll part company with points and vectors being only different in notation. They'll have way different properties. Two vectors in Rn, say vector v and vector w. So these vectors have n components each, are said to be equal if each of their components are equal. So two vectors are equal when their first components are equal, when their second components are equal, and so forth. The zero vector, denoted with a little arrow over it, is the vector, all of whose components are 0. So here's some potential for confusion because there's also 0 the number, 0, the additive identity. So it's important when dealing with a vector 0 to indicate with a little arrow. The book will indicate this by making that a boldface font 0 versus a non-boldface font 0, which they would use to represent, of course, the number 0. All right, so the way Fraley and Beauregard get the ball rolling here is to appeal to your experience maybe with physics. In physics, you're used to describing forces as vector quantities. They have both magnitude and direction. Maybe you've dealt with position expressed as a vector quantity. Then the rate of change of position becomes a vector quantity, that's velocity. The rate of change of velocity is a vector quantity, that's acceleration. So if you've had some physics background, then you've dealt with treating certain physical quantities as vector quantities before. Forces we'll call particular attention to, because if you've got some physics background, you've added vectors together. You've added forces together. And we're going to use that behavior of the way forces add together to give us a definition of how to add vectors together. So we can take whatever definitions we want, as long as they make sense and are consistent, but we are taking our lead from a physical model. In terms of vectors and points in the same setting, we have the following geometric interpretation. All right, vectors are what we're told they are, what they're defined to be, in other words. But I really want to draw pictures. And as long as we have vectors in Rn, and as long as n is maybe 1, 2, or 3, so I can visualize it. I can't visualize very well beyond 3 dimensions. I might have a little bit of success with some analogous behaviors with lower dimensions. But if I want to draw pictures in 1 or 2 or 3 dimensions, then drawing those pictures, it will be what, and this is more my terminology, we'll call it geometric interpretation. So I want pictures of vectors. Consider the vector v in R2. All right, so I could draw it in the Cartesian plane, R2. This vector can be drawn in standard position in the Cartesian plane as follows. We're going to take vector v with components v sub 1 and v sub 2. First component v sub 1, second component v sub 2. Let's associate that vector with the following picture, this picture on the left. We're going to put a point at the origin, a point, we're going to consider the point v1 comma v2, the point v1 comma v2. How can you tell it's a point? Because I use parentheses. So the little black dot here indicates the point with coordinates v1 and v2. And then we're going to draw an arrow from the origin to this point with coordinates v1, v2, and this gives us a geometric interpretation of this vector v with components v1 and v2. Components for the vector, coordinates for the point, and a picture that relates the two. So there certainly is a natural geometric relationship between points and vectors. And this is that relationship. And this was called putting the vector in standard position. So you drew an arrow to represent the vector. You put the tail of that arrow at the origin of the coordinate system, and you put the head of the arrow at the point whose coordinates are correspondingly equal to the components of that vector. In other words, point v1, v2 indicates the head of the vector v with components v1, v2 when the tail is placed at the origin. Oh yeah, but your physical background tells you, well, vectors don't really have a location, so I can't tie them down to putting them in standard position. I ought to be able to put them anywhere and they're the same vector. Vectors in Rn will have magnitude and direction, but not a location, which you want to interpret as, well, that means you can put them anywhere for the sake maybe of drawing pictures like we just did. But I could put them in positions other than standard position, I could take this same vector v and translate it over to point P. In the picture on the right, we've got point P in green. We've got the same vector. The idea being it's an arrow that's got the same length in the same direction. It's just been moved from standard position over to this point P, moved. It's been translated over so that its tail is now at point P. Hey, where's the head of this vector v? We should be able to figure that out. If I knew the coordinates of point P, I bet you I could figure out the coordinates of the point at the head of the arrow drawn here. But on the right, we've got vector v translated to point capital P. Try to follow standard notation. Points are usually indicated with capital letters. Some other things as well, matrices, for example. But for now, it's standard to indicate points with capital letters. Both of these pictures represent the same vector. They're both vector v. If I wanted to talk more about points in this right-hand setting, then we could consider a picture as follows, maybe not necessarily meant to overlap with the previous pictures, but here's a vector in R2. It's got its tail at the point x1, y1, x1, comma, y1, the coordinates of this point. Its head is at the point x2, y2, the coordinates of that point. And the vector is, what would the components be? Well, the first component would be the distance from here to here. Second component would be the distance from here to here along the y-axis. Reminds me of slope. Vectors don't have slopes. They have directions, it turns out, but not slopes. Though I'm certainly reminded of slope in this setting. Yeah, that's because we're in the Cartesian plane. But we'll define this vector to be the vector from x1, y1 to x2, y2, those points, as the vector with components x2 minus x1, comma, y2 minus y1. So we're measuring a horizontal displacement and a vertical displacement. And order is going to matter. In this picture, it goes in the positive x direction and in the positive y direction. Well, it could just as easily go in the positive x direction and the negative y direction. Order matters, but this difference in order will take care of any negative components that might arise. All right. We could certainly extend this to vectors in Rn and points in Rn in the obvious ways. I just have maybe up here in this first picture, if we did this in higher dimensions, then the points would have more coordinates. You want to do it in 5 dimensions? Okay, the origin would be 0, 0, 0, 0, 0, that's 5 components. And we go to the point v sub 1, v sub 2, v sub 3, v sub 4, v sub 5. And then we would have the vector with components v1, v2, v3, v4, v5. We could translate, we could find vectors between points in higher dimensions. Yeah, if it was 5 dimensions, you'd have 5 coordinates here and 5 coordinates here and 5 components here. Otherwise, still taking differences of, it's always difference of coordinate at the head of the vector minus coordinate at the tail of the vector. That's the order that happened. It was x sub 2 minus x sub 1, y sub 2 minus y sub 1, maybe z sub 2 minus z sub 1 if you were doing this in 3 dimensions. Okay, so here comes some of the algebra in linear algebra. Again, motivated by physics concepts. In physics, forces are represented by arrows, better yet vectors, and they throw that term around in physics, maybe without a clean definition of it, but that's our job. If we have 2 forces, say F1 and F2, and these are applied to an object, so imagine a mass sitting at this point here, and we were to hit this object with force F1 and hit it with a force F2, that would be equivalent to hitting it with a single force F1 plus F2, and that sum of those 2 forces will satisfy this parallelogram property, Parallelogram Law of Addition, we'll call it. So physically, forces behave like this, and to take force 1 and force 2, we'll create this parallelogram, introducing a side at the top that's parallel to this bottom vector, and a side on the right that's parallel to this left-hand vector. Create a parallelogram, and then the diagonal of that parallelogram gives the sums of those two forces. That's an experimental physical way that forces behave. Well, we want our stuff to be useful, so we're going to introduce a way of adding vectors motivated by this behavior of forces. We could take forces and scale them. So we'll do that with our vectors as well. We could take vector v and multiply it by 2, double it. I just double its length. If you want to think of vectors in terms of being arrows with magnitude and direction, that'll be fine. That'll get you through probably 90 to 95% of this class. But there's some real important stuff that happens in that other 5 or 10%. Vectors are not always arrows. They don't always have magnitude and direction. In a class at this level, the vast majority of them will. But I would be remiss turning you loose on the world with you having thinking that vectors always are just arrows and magnitude and directions. There's some really useful applications. You ain't seen them yet because you need this background for one thing. But there's loads and loads of applications involving vectors where the vectors are not arrows. They might be functions, for example. If you've taken differential equations, you may have encountered this. If you're taking this, I suspect either you've already had DEs or it's in your near future. And you'll see situations where it's awfully convenient to treat functions as vectors. But for us, the majority of the time, arrows and magnitude and direction. So we want to double a vector, just make it twice as long, keep it same direction. You want to multiply it by -1, reverse the direction. You want to multiply it by -2, reverse the direction, and double the length, for example. So these are the things we're going to do to vectors. In fact, this one slide here contains, this one page contains the two things we'll do to vectors. We're going to add them together, and we're going to multiply them by numbers. And that's what you do to vectors in linear algebra. That's what linear algebra is adding vectors together and multiplying them by scalars. So to formally define vector addition, here we go. Let vector v have components v1, v2 through v sub n. Vector w have components w1, w2 through w sub n. So these are both vectors in Rn. Let R be a scalar. Remember, we're just introducing this term scalar to indicate number. I don't know the history on that, but in linear algebra, you got two things. You got vectors and scalars. The scalars are numbers. For us, they're real numbers. Some folks might want to use complex numbers. There's some benefits to that. Chapter 9 of the book covers complex scalars. And for us, the vectors, at least in the first two chapters, will be vectors from Rn. So they'll look like this. There'll be square brackets and a bunch of numbers, those numbers being called components of those vectors. All right, so we're taking two vectors and a scalar R, a number R. We're defining the sum of two vectors, v and w, v plus w, vector v plus vector w to be. The vector within components, the first component of which is the first component of v plus the first component of w, v1 plus w1. The second component of which is the second component of v plus the second component of w, v2 plus w2, and so forth. So you just add the corresponding components together. So a sum of two vectors is a vector. By the way, it's revealed down here, so spoiler alert, this definition of vector addition gives that parallelogram property we saw on the previous page about drawing parallelograms and the sum being the diagonal of the resulting parallelogram. This is what makes that work. Vector subtraction, some books might leave this out. It's a touch redundant along with scalar multiplication, but they'll define vector v minus vector w to be the vector with n components, the first of which is the difference of the first components, the second of which is the difference of the second components, and so forth. So v minus w, quite similar to v plus w. And finally, scalar multiplication, r times vector v. Here's vector v, it has components v1 through v sub n. Then we'll define scalar r times vector v to be rv sub 1, comma, rv sub 2, comma, and so forth, up through rv sub n. So it looks like you just took this r and you distributed it. But this ain't distribution. Distribution is a different thing. This is a definition of scalar multiplication. So these are the definitions under which we operate. These are putting an algebraic structure on Rn. You don't do that with points. You don't add points together. You don't multiply points by scalars. Now we got a difference between points and vectors. We can add vectors together. We can multiply vectors by scalars. You can't do that with points. Points got nothing but a location. And informally, vectors, they don't have a location. They got a magnitude and a direction. Vectors in Rn do. There are exotic vector spaces where that's not the case. The vectors don't have magnitude, for example, and direction is kind of an informal concept, but it's a useful one for us to think about in terms of pictures. But this is not distribution, it's a definition. So you can't argue with any of this, it's a definition. It's motivated by the behavior of forces, say, from physics. So there's motivation on this definition, so we'll be able to use this stuff to model physical problems. Some more pictures in terms of how you might interpret this. Vector v plus w, we could view that with the parallelogram law of addition. An alternative idea is you want to look at vector v plus w. We could take vector v, draw the little arrow that corresponds to it, then take vector w, place it at the tail of vector v, and then draw that arrow. And the resultant is from where we started to where we ended. That's vector v plus w. What they're getting at, to give you some clues on how Fraley and Beauregard are thinking on this stuff. These are vectors. These three things are vectors, right? Vector v, because it's boldface font. Vector w, boldface font. What's the zero vector there? Because it's a boldface font. So what they're going to do in the book is whenever you see this boldface zero in a little picture, they're implying that they're putting these vectors in standard position. They can be anywhere. Well, let's put them in standard position since they can be anywhere. Standard position is the only way to go if you want a geometric interpretation. But we could just as well take vector w and translate it up and draw v plus w and then get the resultant v plus w. Or I guess for that matter, we could take v and then translate the w over. Take w and translate the v over. Then we have w plus translated v. And of course, we get the same thing as the resultant. When you take differences, and one thing I could do is reinterpret this w maybe as a negative w and then use the parallelogram law of addition. But if we were to take vector w and multiply it by -1, it'd point off in the left direction. Same magnitude, opposite direction. If we'd use a parallelogram law, then with negative w in vector v, it would produce this v minus w vector, which can also be translated over and interpreted like this. When you take a difference of two vectors, v minus w, underneath this is some sort of parallelogram law. What it is you'll draw the parallelogram containing v and w. Vector v minus w will be the other diagonal of that parallelogram. This diagonal, starting over here at the zero vector, that'd be the sum. The difference would be the vector that runs along the other diagonal of the parallelogram. And direction matters. We've got v minus w. Vector v minus w will have in this interpretation its head at the head of vector v and its tail at the head of vector w. So I could orient it in the other direction. If I did that, we'd have W minus V. So there's a geometric way to interpret a difference of two vectors. That's why they've introduced it in the definition, I suspect. We don't really need it. Specifically, we could get away with scalar multiplication being defined in vector addition. But there's a way to interpret the things which Fraley and Beauregard have defined in terms of vector addition and vector differences. Let's illustrate it. Quick little comment here. When I refer to an example or a theorem in these notes, if I have in blue, if I have the fonts in blue to indicate it's theorem 5 or examples, then there are the supplemental notes illustrating that. So here we are in the supplemental notes for section 1.1. And we'll outline, we could in these notes, and I mentioned this is all the stuff is online. If I'll click on this one, it'll jump to that problem, which maybe we'll do later. But right now, let's just go through and illustrate simple vector addition. Compute the linear combination, a word to be defined deeper in the section, but we need to do some examples now. I've stated the question as it appears at the end of the section. The linear combination, 3u plus v minus w. All right. I want to say we only do two things with vectors. We add them together and we multiply them by scalars. Fraley and Beauregard are saying we do three things with vectors. We add them together, we multiply them by scalars, and we take differences. I could take a coefficient of -1 up front here and convert the vector subtraction into vector addition along with some scalar multiplication. So technicalities, but the big picture is we do two things to vectors. We add them together and we take linear combinations. That'll be a big concept later on when we know more stuff. So find that vector. What happens when I take 3 times v plus 3 times u plus v minus w? Where u, v, and w are given as these vectors. Okay, straightforward computation. We'll go through and tediously justify each of our steps as we are obligated to. It's a math class here in the beginning. This will get old fast and we'll start taking more intuitive jumps, but in the beginning we'll justify every little step. Some observations. Vectors u, v, and w each have 4 components, so they're vectors in R4. We have defined scalar multiplication, vector addition, and vector subtraction. Okay, so let's compute 3 vector u plus vector v minus vector w. Here's vector u, 1, 2, 1, 0. Here's vector v, and here's vector w. All right, let's do the scalar multiplication first, because I typeset it that way. Something's got to be done first. I couldn't add these vectors together because the scalar multiplication is in the way. I could take the difference of these two first if you wanted to. But let's take care of the scalar multiplication first. All right, that 3, what was it again? Is it the distribution? That ain't distribution. It reminds me of distribution. Distribution is, you know, multiplication distributes over addition. Well, there ain't any addition right here. There's some addition elsewhere in the problem, but right here, you're simply taking that vector and multiplying it by 3. You're not distributing because there's nothing to distribute over. It is a vector. If there was some addition inside, sure, and we'll see some distributive properties. This ain't one of them. This is a definition of scalar multiplication. If in your head you want to think of it as distribution, just don't tell anybody and don't let me know about it. But conceptually, you take the 3, it goes onto each of the components, and it certainly looks like distribution. I wouldn't bring it up other than it's so easy to confuse it with distribution. Computationally, take that 3, put it on each of the components, simplify 3 times 1, 3 times 2, 3 times 1, 3 times 0. Who justifies this manipulation? Why, that's the definition of scalar multiplication. We stated it with an r as the scalar, and r went on each of the components of the vector in that scalar multiple of the vector. Okay, so we get this, simplifying produces this. How about we add the first two together? Let's do the vector addition first. You want to do the vector subtraction first, that'll be fine. I didn't typeset it like that. So we'll take a difference, we'll take a sum of corresponding components. Doing the vector addition first, says who? First formal definition we had, that's how you add vectors. So we'll have 3 plus -2, 6 plus 0, 3 plus 1, 0 plus 6. There you go. There's the vector sum. We'll still take subtraction by this vector over on the right-hand side, but who says you do that? Definition of vector addition says you do that. Let's simplify. 3 plus -2 is 1. We get a 6. 3 plus 1 is 4. 0 plus 6 is 6. We still got this thing sitting over there. And now let's do the vector subtraction. You subtract corresponding components. No surprise there. Simplified, it looks like you get the vector -2, 11, 3, 8. So that's how you take linear combinations of vectors. Straightforward stuff. We're going to do a bunch of this. We're going to do a bunch of other stuff, way more complicated than this. But linear combinations, though not formally defined, linear combinations of vectors is so fundamental to this course. It must be linear combinations because this is linear algebra. It's the algebra of vectors is what it amounts to. Let's look at another example. Number 14, okay. This one's a little unclean. It would make an awful test question because it's subjective. It's a good question, other than that, because I can draw pictures and it indicates how to interpret the things we do to vectors. Two things, multiply them by scalars and add them together, I say. It says reproduce, the question in the book is stated as reproduce the vectors in this figure and draw an arrow representing the vector -3u plus 2w. Okay, here's u and w. My picture's just as good as the one in the book. They have some pretty low quality graphics in this book. It's an excellent book. The graphics could use a little work maybe. I don't know anything, and this looks quite similar to the picture from the book. I don't know how long these vectors are. I've got to eyeball it. That's why these are awful test questions, because it's so subjective. But let's see what we can do here. They want -3u plus 2w. Okay. Well, what's 2w going to look like? Well, that'd be a vector in the same direction as w, but twice as long. How about -3u? Well, the negative would reverse the direction, have it point in the opposite direction, and then the 3 would triple the length. So I claim 2w looks something like this. Here's u, -3u, opposite direction, 3 times as long, should look something like that. Eyeballing it. Okay, so we want to add those vectors together. How do you add vectors together? Geometrically. Oh, and by the way, these vectors are in standard position. Their tails are at the origin of presumably a coordinate system. Add vectors together using the Parallelogram Law of Addition. So I'll draw a parallelogram, and then the diagonal of that parallelogram will be the vector sum, 2w plus -3u. And that's what they were looking for. They were looking for -3u plus 2w. Same thing. So we'll get out this diagonal. Should it have been horizontal? Who knows? The graphics just aren't clean enough to determine if it should be horizontal. I just eyeballed it, and my little picture looks like I don't quite get a horizontal vector. Maybe you do. I'd have to measure things and do things precisely. That's not the point of the problem. The point of the problem is, how do you geometrically interpret multiplication by scalars and sums of vectors? Multiplication by scalars are stretching things. Negative scalars stretch things and reverse the direction. And vector sums. Vector sums are this parallelogram law of addition stuff. So let's take a little break there in the middle of section 1, and I'll be back. And we'll finish up section 1 and actually prove some properties of vector addition and scalar multiplication. I'll see you there.